right. Good morning. I'll start recording the homework. The homework to do is over there. Please make sure I hear that you are here. Robbie L. Daniel D. Thank you. Daniel Durekam. Spencer Hunt. Swansea Sue. Jason Yang. Thank you. Annie Ruth D. J. M. Sorry, I can't read it. Denis Mezanovic. Wei Wei Chen. Rodion. Thank you. Sunat S. Jeffrey D. Jeffrey D. Sam Brock. Andy Peruca. Morgan K. Thank you. Lee here. Carson Cook. Here. James K. Here. David Drost. Here. Shanghai K. Here. Thank you. Jeremiah Pesca. Here. Alec Moore. Ivan Johnson. Here. Lee Hong. Here. Tristan A. Here. Janak A. Janak. Janak. Yeah. Is this one? Cameron M. Beren. Unan R. Ray Emery. Duanil Chosky. Bailey Johnston. Mel Flygert. Mel. Here. Kobe Davis. Here. Andrew Gonzalez. Here. Frank Sun. Connor K. Connor. Tim Coutinho. Yeah. Hannah Fangley. Daniel Persson. Boxwan Zhang. Huang Kim. All right. Anyone has the homework to turn in? All right. All right, I got some addition to the open books one on YouTube that Carson sent me, and is I think it's pretty good. If you look at the comment, all the comments are that these are much better than the instructor. So maybe you should go there. Not me in particular, all the instructors that the student had. All right. Thank you for sending it. Schedule today's homework 4 is due today. And the next one is due on Wednesday because we are catching up the snow days. Any comment, question about the organization of all this? Everyone all right, comfortable? All right. So last lecture we did permutation, combination, with and without repetition. Should I address anything of that? Do you have any question? Yes?
There was one on the homework where it was like you have like 7 objects and
Yes.
3 spaces, and you have to have one of the objects in
Yes.
spaces. Can you go over a problem like that?
This was due today?
No, one today. But just some similar, it doesn't have to be the same.
All right. So, I'm sorry? Yes. So here you have your object, right? And here you pick some object on those, but one has to be fixed. So what is a way of doing this? Someone has any idea? There are many ways, I guess. One is, yes?
You just take out one of the spaces and one of the objects.
Close.
You do that, then you do it 3 times because it has a position in each of the possible 3.
Exactly. So I would say, forget the one that you are forced to put there. Forget it for a second. Do everything else. Now you have to put the one that was left there, and where do you put it? In every possible position. Right?
So
All right.
when you solve it, though, you solve with 2 spaces instead of 3, and then you act like you do that other stuff after.
So I think that here, if you have to put the 3, and one is fixed, you decide how to put the 2. And then the fixed, where can you put it? At the front, in the middle, or at the end? I think also it's not too difficult to check because you can probably write all the possible cases without too much trouble. Did anyone try to write the programs to compute the permutation or combinations? Yeah?
For one of them, I don't remember which one.
And was it easy? Was it difficult?
It took a couple minutes.
I guess you had to do it with recursion, right? Or you didn't?
No, I don't remember which problem it was after that.
I think with recursion probably is easier, but all right. Should we move on to the new subject? Any other questions about permutations and combinations? All right. So we start a new section which hopefully will be interesting. We talk about probability. And probability came about 1600 and 1700 when, particularly in France, the government built casinos where people can go there and gamble. And so there was quite a bit of study to make sure that whoever owned the institution is not going to lose money. All right, so let's see what are the elements of the problem here. We have a set, and like every time we are in a specialized domain, we change the name of the set and the element of the set. You may remember that when we talk About alphabets, the elements are characters. When the elements are words, we say that is a language. When the elements are pairs, we say that is a relation. And so here we call the set a space, and the elements of the set are called points. These are just the names for a set, and the elements when we talk about probability. You can call it a set and element, and that would be fine. So we have this set. The key piece is a function, which is called a probability distribution. The probability distribution is a function. The domain of the function is the space. The codomain is the real interval between 0 and 1. The extreme are included. And this function has a requirement. When you add the value of the function over all the elements of the space, the sum is 1. Yes, you can put it here. Thank you. All right? We are going to see an example in a second. First, I tell you the concepts, and then we see them in an application. All right. A subset of the space is called an event. A subset of the space is called an event. And the probability of an event, now we overload the function. The function is overloaded because it takes elements or takes a set of elements that we call event, and is overloaded in a very nice way. The probability of an event is the sum of the probability of every point of the event. So let's look at an example. My space are the numbers, integers between 1 and 6. If you want a model in your mind, this is what is happening when you throw a die. You get one of those values. The probability is 1/6 for any one of these. And now we verify that that one satisfies the condition. First, the value is between 0 and 1. And when you add all the values for all the points of the space, you get 1. All right? An event is the set 1, 2, which is a subset of the space. If you need a model in your mind, you throw a die, and the top face is either 1 or 2. What is the probability of this event? Is the probability of 1 according to this function plus the probability of 2 according to this function. All right? So, it's pretty simple. We have those 4 concepts: space, probability distribution, event. And here you see a simple example of this. Let's look at another example. You throw 2 fair dice. Fair, what does it mean, fair? I didn't hear. You are not cheating, right? You didn't do something so one face come up more often than the other. And so the probability of each face is 1/6, as we did before. So the event is the sum of the 2 dice. When I say sum of the 2 dice is the top face, is 7. I think if you go to Las Vegas and you play dice, when you get the 7, you win. And so here, I want to know what is the probability that you throw and you win. One in 6. How do we compute this one? First, we have to represent the space, right? And so this is the first, and this is the second. Here you get 1, 2, 3, 4, 5, and 6. This represents the situation in which you draw and the first dice is one of those values. The second also has this one, right? 1, 2, 3, 4, 5, and 6. And so this corresponds to the situation where you get a 1, 1, the two faces. This is 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. You with me? I'm just representing the situation. This will be 2, 1, 2, 2, 2, 3. This will be 3, 1, and so on. So now I want the sum of these two to be 7. So which are the cases? 1 and 6. This is a 7, right? Then I will have 2 and a 5, 3 and a 4, 4 and 3, 5 and 2, and 6 and 1, right? These are all and only the one that will give you 6. 7, thank you. So, how many are they? 6 out of 36, right? And so the probability is 6 out of 36, which is 1/6, if you simplify. Far so good? All right. Let's look at another example where we can apply the things that we learned at the previous lecture. Oh, you are not seeing it? So in the game of poker, you are given 5 cards. 5 cards. And a very desirable combination, and we will see in a second why this combination is desirable, is that you have 4 cards of the same rank. Same rank means that these are 4 aces, or 4 kings, or 4 7, or 4 twos. And the other card is anything you want. So we would like to compute the probability that you are given 5 cards and you have a 4 of a card. How would you go about this? I'm sorry?
Calculate the distribution out of any hand with any set of numbers, and then you pick and choose which one would actually be the...
Right. The probability will be exactly what we did for the dice. You count all the possible ways that you can have the 2 dice, and you count all the cases that are favorable, the one you are interested in. So here we can count all the possible ways to get 5 cards, all the possible ways that in these 5 cards you have a 4 of a kind. We divide and we know. So here we can make a decision when we do this. And the decision is, when I give you a hand, when I give you 5 cards, does it matter which card do I give you first or not? Well, we can go both ways, right? If I give you the card and you pick one, and you pick the first, the second, the third, the fourth, and the fifth, good players typically do that. They don't start to put it in position because this can give some information to the opponent. And so, if you get an ace and then a king, is different than if you get a king and then the ace, even if they are the same, right? So they were given to you in a different order. For the game, the order is not really important. 4 of a kind, it doesn't matter when you put it on the table which order it is. So we can do it in one way and we can do it in another. It's an interesting exercise either way. And of course, we expect at the end to get the same answer. So here I start by considering the order. All right? So it matters which card I give you first, and which card I give you second, and which card I give you third, and so on. Yeah? And so, in how many ways can I give you 5 cards? As a reminder, a deck has 52 cards, and they are paired in 4 suits and 13 ranks. The 4 suits are club, diamonds, hearts, spade, and the ranks are 2, 3, 4, 5, up to 10, and then you have jack, queen, king, and ace. 13. And so you can pick the first card in 52 possible ways, right? The second in 51, and then 50, and then 49, and then 48. Right? These are the permutation of 5 cards out of 52. Here I consider the order. If I don't consider the order, this would be what? 32 choose 5, the binomial. So if I consider the order, how many hands there are? About 312 million, right? Quite a bit. So this was the easy part. Now we have to figure out how many hands have a 4 of a kind, and the order of the cards is different, right? So how do we do this one? So there are 13 possible ways of having 4 of a kind, right? Whether it is a 2, a 3, a 4, a 5, up to a king. So 13. For each one, if I consider the order, there are 4 factorial permutations. Depends whether club is the first or diamond is the first, and so on. Yeah? So I have this one. Then I have the remaining 5th cards. There are 48 possible ways because is the number of cards that remain after I pick the 4 of the same rank. And doing exactly what we did a second ago, this one can be the first, or the second, or the third, or the fourth, or the 5th. And so if you consider the order, there are about 75,000 ways of having 4 of a kind. If you consider the order. If you don't consider the order, the number is much smaller, but again, it's much smaller the number of hands. And so, now we divide this by this, and this is the probability that when you are dealt a hand, you have a 4 of a kind, which is 2.4 out of 10,000. And so, it's not very likely, right? It's not very likely that you get this. And this is why it's a desirable combination. And ranks higher than most any other. Yes?
And so when you're talking about the 4 of a kind band,
Yes.
the reason that you make the order important is so that you don't artificially reduce the amount of chances you have to get your
So we could do it in the other way, right? Suppose that we don't care about the order. So, what do we have? What is the number?
for which part?
To have a 4 of a kind if you don't look at the order.
4?
So, you pick the rank of this one. So you have 13 ranks. Yes? The order of the card doesn't matter. So once you pick the rank, you're done. And what about the remaining card? How many ways you can pick the remaining card?
48.
48. And there you have it. And so, if you don't look at the order, we found how much is this, how much is this. 5 choose, 52 choose 5. maybe we should remind what is 52 plus 5 is 52 factorial divided by what?
5 factorial times 52 minus 5 factorial.
Fantastic. Which is the formula that we looked at last time. So far so good? And so, in a similar way, you can compute, for example, a full house, which is the combination of 3 cards of one rank and 2 cards of the other rank. Or you can compute a royal flush. A royal flush is ace, king, queen, jack, and 10, all of the same suit. How many royal flushes there are? 4, right? Very good. All right.
Could we make another example like one of those?
Say that again.
Could we make another example like one of those? The Royal Flush
Also, it's somewhat trivial. I don't even know well what to write. So, a royal flush is ace, king, queen, jack, and 10. All right, all of the same suit. So, how many suits are there? 4. So, there is a total of 4 royal flush, disregarding the order. And so, the number of hands disregarding the order is 52 choose 5, which is 52 factorial divided by what? 5 factorial and is 47 factorial, right? And so you divide this number, and this is the probability that you get a royal flush.
So divide 4.
Say it again.
Divide 4.
4 by that number, which is relatively large, and so the probability is quite small. So basically, I think that if you want to understand this, this is really the good example, because this is easy to understand. And so this one says, look, the probability is that the one you are considering, in this case was a 7, divided by O. I think if you get 2 or 12, you lose right away. So what is the probability of getting a 2 or a 12 when you throw 2 fair dice? Two out of 36, because there are 36, right? 2 is that corner, and 12 is this corner, and there are no others. So there are 2 out of 36, which is 1 out of 18. All right? We are going to do another example, a little bit more complicated later. Actually, we'll gamble and see whether I win or you win. I'm sorry?
If you win, we give you praise.
Good point. And if you lose?
Then
If I win? All right. So, some properties of this probability function. Says, look, no matter what is an event is a subset of the state. The probability of the event is between 0 and 1, inclusive. So if we look again at this example here, who can tell me what is an event whose probability is exactly 0, the probability is exactly 1, and the probability is in between 0 and 1, and neither of both? Yes?
For 0 probability, roll like 13.
Right, that you get a 13. You are not going to get it. It would be a miracle, right? And so, In science, the probability of a miracle is 0. In life, I let you decide according to your religion. Alright, so here we saw an event whose probability is 0. Who can tell me an event that the probability is 1?
You get 2 numbers.
Say that again?
Roll the dice, you get 2 numbers.
Well, 2 numbers. You have to be a little bit more precise.
Roll between 2 and 12.
Right. You get between 2 and 12. And so this is a certainty, right? Unless the dice stands on a corner. All right. What the probability in between 0 and 1? This one that we saw, this one is 1/6, which is greater than 0 and is smaller than 1. So you have the example there already. All right. And so this one is the first. It says, look, the probability of an empty event is 0, and the probability of the entire space event is 1. We just look at an example of those. So they should make sense, right? The probability of the space take away an event, this is set difference, that minus is a set difference, is 1 minus the probability of the event. So let's look at this on this easy example here. What is the probability that you don't get a 6 when you throw 2 fair dice? Yes, thank you. You don't get 7. Right, someone said 5 and 6. Why? Because the probability of getting a 7 is 6. Of not getting a 7 is 1 take away 6. 1 take away 1 6. All right. And so the last one is an application of inclusion-exclusion that we saw at the beginning of counting. It says the probability of the union of 2 events is the probability of one plus the probability of the other. Take away the probability of the intersection. Why the probability of the intersection? Because we counted twice. We counted in the probability of 1 and we counted the probability of 2. All right? Very good. Do we need a recap or everything is under control? We need feedback. All right, everything is under control. I mean, these are not terribly difficult concepts. So now something a little bit more interesting. Expected value. We study this to compute the average running time of an algorithm. Average. Typically, the way we saw it is a worst case. Why? Because this is the maximum time you have to wait for your result, so you want to know, you want to put limits. If an algorithm run fast enough and you run it a long number of times, you run it every day or many times every day, then you are more interested in the average. Maybe the worst running time is long, but most of the time will be shorter, so is a gain if you have a lower average running time. And so we do this one. Instead of doing for an algorithm that is very complicated, I do it for gambling, that probably you find it more interesting, and it's certainly much easier to understand. So I do this twice. One is here. This is roulette. In this country, you have 2 zeros, which are green, and then you have a 36 number between 1 and 36, half of which are red and half of which are black. And so you can gamble that the next time you spin the wheel, you will get either red or black. If you get what you choose, you win 1. If you don't, you lose one. The fact is that 0 is green, so when you get 0, no matter whether you put red or black, that's lost. This is how the house can keep up the casino and the maintenance and pay the people that are there and pay electricity and maybe free drinks if you lose a lot and all that. All right? And so, how do we compute this one? Here we have two things. Let me write it here. There is a reference in the note for all this, so it's expanded well enough. So here we have two parameters. One is a probability function that goes from the space into the interval 0, 1. All right? The other one is a value, v. This value goes from the space into whatever is appropriate. In our case that I'm going to discuss now are the integers. But just to be general, we put the real. So this is a function that can take anything you want. A real number can be positive and can be negative. Typically we have a viewpoint, so this will be your viewpoint. If money is coming in, this is positive because it's a win. If you lose money and you give it out, it will be negative because you lose. All right? And so the expected value is the following. Is the summation x in the space of what? P of x times v of x. What is this formula try to capture? V is how much you win or how much you lose. This can be a small number or a big number, not the same for every point. On the other hand, if it is a big number, but the probability is low, you will not get this often. So you may do well even if once in a while you lose a lot of money. And so this is how you get the average performance of an algorithm. For some input, maybe the algorithm is going to make a lot of operations. But if this input comes very seldom, then you are going to execute those lot of operations only very rarely. So you don't care that much. Yes?
I'm trying to just clarify the top line, what the syntax is saying. So you've got the space s with values 0 and 1, and then p is the probability.
So this is the notation of a function. Let me go back to the slides because this may stimulate your memory. If we go to the slide schedule, where yes, thank you. If we go to the schedule and we look about the functions, this is the notation. You remember the notation here? F is the function, A is the domain, and B is the codomain. All right? So, if I junk this one and we look at what I wrote here, P is the function, S is the domain, and this is the codomain. This is the real interval between 0 and 1 inclusive. All right? So, now, let's go back to the problem we are trying to solve. Yes?
And you're doing the inclusive range of 0 to 1 because it could be like 0, 0.0003, like it could be all the real numbers.
Can even be 0.
Yeah.
And we saw an example where the probability of something is 0 means it's not going to happen, or it's a miracle. All right, so if we go back to this one, what are the outcomes? Suppose that you put a chip, $1 chip on a red. All right? What is your space? Your space is red or black?
Agreed.
Or green. Very good. Or green. So, when we do this one, let's do S is red, black, and green. So what is the probability of red? Here I put the probability below. What is the probability of red? 18 out of 38. Yes? What is the probability of black? Same. What is the probability of green? 2 out of 38. What is the value of red? 1, because you put a chip on red. If red comes out, you win 1. What is black? -1. What is green? -1. And so now we do the summation. 18 out of 38 times 1 plus 18 out of 38 times -1 plus 2 out of 38 -1. And so this is the expected value. This is what you should expect if you go there and you play an afternoon. And so you do the computation. I'm not going to do it. You read it there. And so this is -2 out of 38. Let me move the window because you are missing the last point. This is about a negative 5.26%. So 5.26 of a dollar is more or less a nickel, right? And so your expectation is that every time the wheel spins, if you play red, you lose a nickel. This means that now you lose $1, now you lose another $1, now you win $1, now you lose another $1, but on the long run, you will lose about 5 cents every time the wheel spins. This is the expectation. All right? And so, you know, this means that you can also win money. You go there and you put $1 on red, the red comes, you win. Or if you put $1,000 on red. But the idea is not that you shouldn't play a day. Because if you play a day, this is going to catch up with you. Instead, you put $1,000. If you are unlucky, it's like you spend all day and you lose it. And if you are lucky, you get $1,000, you should run home because otherwise you are going to lose it. All right? So, let's do another one. In this case, I bet with you. All right? So, from your viewpoint, we draw 2 fair dice. If the outcome is 7, you win $100. I'll give you $100. Right? If the output is 2 or 12, you lose $100. All right? Anything else, you lose $10. You give me $10. All right? So, will you play with me or not? So, I think you answered a little bit too quickly. Why don't you compute? So first, what is the space? I'm sorry? Well, really, you only have these two, right? So why don't we call this event 1, event 2, and event 3? And so, here in the summation for these 3 events, it really doesn't matter if you get a 7 with 1 and 6 or 4 and 3. So now you have to add together what? the probability of an event for the value of that event. You add all of them together with the sign depending whether you win or lose. Yes?
So in this case, do you have to roll the 2 or 12, or does the order not matter?
The order doesn't matter. If the 2 or 12 is coming up, you lose $100. You know the joke. It says, what time is it? It's 12 and 14 minutes and 22 seconds. And you say, can you please be more precise? It's 12, 14 minutes and 22 seconds, you idiot. So, are you going to play with me or not?
Yes.
Ah, good. Good. So, should we do it? Yes. So here I have the summation over what? Event 1, event 2, event 3 of what? Probability of event I times value of event I. Yeah? Where I is equal 1, 2, and 3. So what is the probability of event 1? 1/6. And here you win $100, right? Plus, what is the probability of event 2? Here I had 118. I like it. 118. And what is this? Minus 100. Plus, what is the probability of event 3? Say that again. So here we take 8 out, right? 36 and take away 8 is 28. So this is 28 out of 36, which is 14 out of 18 minus 10. Yeah? So let me change this also into 18s. So this will be 3 18s. Am I right? And so this will be 300 minus 100 minus 140 out of 18. And what is this one? 60 out of 18. What is 60 out of 18? Whatever. So if I divide by 6, this is 20 and this is 3. And how many times 3 is in 20? About 7?
Divide by 6 is
10. All right. So this is 3.33. And so every time we play this game, you win $3.33. This is what you should expect. So you should have gamble. Why you trust me so little? But if I make an offer. Yes?
So this is, given that this is a class on computing, we assume that this is an arbitrarily large number of trials. In smaller cases, let's say you only have 10 times that you gamble, you can't assume that we'll crush that average.
Right. So this is statistics and we don't go there. We stop the probability. All right. Will we take 10 minutes break? All right.